Great. Well, I'd like to join in thanking the organizers. This is a very stimulating meeting. The issues are fascinating. And in the spirit of complementarity, it's a pleasure to follow Jose here. You'll hear some of the ideas expressed with a slightly different accent, both in English and in science. So these are tricky ideas. Some of them I know are very confusing. So it's a rare opportunity to be able to give these talks back to back. And some of the questions that were asked, you could ask again, and and we can explore them more deeply. So let me get my talk up here. Okay. Right. So I'll continue the discussion of electron tunneling mediated by proteins, and it's great to have had this introduction. So just to follow on the introduction, we're interested in how electrons move long distances. And these could be distances from just beyond van der Waals contact, a couple of angstroms, up to tens of angstroms between electron transfer cofactors. Another thing I should say for the physicists is this problem of electron transfer in biology is a lot like tunneling between defect states in semiconductors, in large bandgap semiconductors. So you can think of our cofactors. In this cartoon, we have a heme protein up here and a heme protein down here. These heme cofactors are the electron traps. And the protein that wraps around them is a large bandgap semiconductor. And the energy gap between these redox active, electron transfer active states from the edge of the valence band is about 2 eV. That creates the tunneling barrier. And a lot of my talk is going to be about the energy and time scales at play to sort of build on what we heard so far. Okay, so I'll talk about electron tunneling. As you're becoming experts on these tunneling pathway arguments, I'll tell you about some ongoing work where we're trying to manipulate these quantum interferences among multiple coupling pathways, a work in progress. And I'll tell you a little bit about a 2-electron transfer problem that's related to flavoproteins. We've heard about them a lot today, and we also heard about electron bifurcation briefly in the reactive oxygen species talk, so I'll connect with that. So here's a restatement of the electron transfer problem that Jose told us about. We had a good question about what the minima of his potentials correspond to. So the offset between the potential minima that Jose told you about reflect the different electron affinities of the electron donor and acceptor. So if you like, the redox potential gap between those two species. So at equilibrium, on average, if I start an electron in its ground state, it will be on a donor species. I may add a photon to photoexcite the species, or I may have another way to inject a high energy electron. And it's through thermal fluctuations in this case that, that those donor and acceptor electronic states, they're symbolized, these are representing electronic state energies, that they come into degeneracy. And it's in that degenerate configuration that my electron can tunnel. Okay, so there's an issue of coherence and timescales that we've been discussing at the meeting. We know that these electron transfer events can be anywhere from a couple of picoseconds in the early events of photosynthesis to days and years. So how is it that we can have coherent quantum phenomena at play? It's because this activated complex that I'm symbolizing up here lives for a very, very short period of time, maybe a couple of femtoseconds. So the coherent phenomena that you saw in the tunneling pathway pictures and the multi-pathway pictures are relevant to that activated complex for electron transfer. Then we relax and form the products. Okay, so it's such a diverse audience, I thought I'd introduce a brief history of these, this issue of electron tunneling in electron transfer and in biology. It was recognized even before the Rudy Marcus theory. There was another discussion of electron transfer by Eyring and co-workers, where already in the mid-50s, it was recognized that for electrons to move between these trapping sites, they have to tunnel. And Rudy Marcus, as Jose said, introduced this as an empirical transmission factor, no detailed quantum mechanics. DeWalt and Chance measured the whole refilling in the special pair down to low temperatures and implicated both electron and nuclear tunneling in those reactions. Hopfield, using some clever estimates associated with the optical properties of proteins, guessed a 2-electron volt barrier for tunneling, not a bad estimate on average. He did some experiments a few years later where he bound redox active species to the surface of cytochrome. Now, these were heroic experiments in the late 70s. They're fraught with artifacts, and so you don't see anyone discussing the numbers from these papers. But I think conceptually they led into the work that Jose mentioned from Harry Gray, where they used ruthenium probes rather than iron probes to modify protein surfaces and explore electron tunneling over fixed distances. So we figured out that the mechanism was hole-mediated superexchange, that these redox states are closer to the bonding orbitals than the anti-bonding orbitals in most proteins. And then, as Jose described very well, explored the through-bond and through-space mediations as well as multi-pathway effects that came later. When you have many pathways, they can interfere coherently. They interfere coherently. They can be constructively interfering or destructively interfering. And we heard about how that can have implications when you need to move the electron really fast. You want to be sure that you're in a geometric pose with constructive interference rather than destructive interference if you're in a rush. And we'll talk about more of these detailed issues. There's been a lot of interest in biological electron transfer in the last decade in systems with smaller tunneling barriers. Instead of multiple electron volts, tenths of electron volts. So I want to talk about that as well. So here's the classic Hopfield Marcus sort of picture of electron transfer. We assume that we have a classical nuclear degree of freedom. If it's a harmonic oscillator with a spring constant k, here's the probability distribution function for positions along the harmonic coordinate. Now, in the case of electron transfer, we don't just have one potential surface, we have two, one corresponding to the oxidized and one to the reduced species. And so we also can calculate the probability distribution function for energy gaps between the reactant and product surfaces. And we can calculate these distribution functions for both the donor and the acceptor. And just as the spatial distribution function is Gaussian, the distribution function for energy gaps is also Gaussian. And so Hopfield and Marcus theories basically calculate the probability of removing an electron with a particular energy from the donor and inserting it on the acceptor and calculating an electron transfer rate as a consequence. And so this integral represents the probability of energy matching, getting to the Arrhenius activated complex. And the prefactor represents the probability of tunneling once you've reached that point, as we heard earlier. Okay, so it's fun to talk about the time scales and energy scales for this audience. So the barriers in proteins are about 2 eV. The magnitude of the energy fluctuation, if you looked at my previous slide very carefully, you would have seen the widths of the Gaussians. The Gaussian widths are related to the thermal temperature, kBT, and the so-called reorganization energy, the Marcus reorganization energy, which in all the systems we've been discussing today are between half an eV and 1.5 eV. We'll take 1 eV as a typical number. So these non-equilibrium fluctuations are on the scale of 1/4 of a volt. That's important. It's 10 times kBT. Okay? Typical couplings at 10 angstroms are a wave number. Okay? So what are the timescales involved? Well, the timescale for being at that Marcus crossing point in that Arrhenius complex is single-digit femtoseconds, just doing a back-of-the-envelope calculation based on the energy level fluctuations it takes to get you up there. The timescale associated with protein fluctuations that cause the coupling matrix element to change value are 10 times larger. And this is why we can do sort of quantum mechanical calculations of donor-acceptor tunneling interactions in a straightforward way without going beyond a Frank-Condon type picture. This is also interesting to discuss. So think of those two hemes on the first slide. If I could lock them in the activated complex so that they're energetically degenerate, the electron would oscillate back and forth, and its frequency would be the coupling divided by h bar. So that's a two-level system. Oops, that's related to a two-level system oscillation time, which is very long on the time scale that you sit in the activated complex. So this energy matching is disrupted over and over and over, millions, billions of times before the electron goes all the way from donor to acceptor. That's what makes these processes non-adiabatic. So those are the key energy and time scales. Okay, so I mentioned very briefly that the barriers for tunneling in proteins are EVs, and in DNA, the barriers are much smaller. So here are my Gaussian broadened energy levels in the gap between the valence and conduction band of a protein. The key feature I want to point out is that these broadenings are 10 times smaller than the tunneling energy barrier. So I don't have to worry about transient resonance of these states through thermal fluctuations with the filled and the empty states of the bridge. Not so in the case of DNA. The typical DNA electron transfer experiments, if you're interested in these, they're a little off topic for most of what I'll discuss today. Those gaps tend to be 1/4 of a volt. So they're on exactly the same energy scale as the energy gaps between donor, acceptor, and bridge in the case of DNA electron transfer. So you should expect the quantum dynamics underpinning DNA electron transfer to be much richer and different from protein electron transfer, okay, for those reasons. Okay, so the tunneling process is coherent. Another energy scale to think about another mechanism to think about that could compete with exponentially decaying tunneling would be thermal injection of carriers to the protein. So why doesn't that occur? Well, if I plug in a 2-electron barrier for injection in a Boltzmann-style expression, I'll find that for typical barriers like we've been talking about, I have to be at distances of 40 angstroms or more before I could inject carriers and compete with the tunneling mechanism through a hopping mechanism. We heard about secondary structure dependence that comes out of the tunneling mechanism. I'll show you some cartoons that reinforce what you heard and might give you a slightly different perspective. We heard that interferences can indeed be important, and in most cases we've looked at for slower electron transfer reactions, as Jose mentioned, the coherence parameters, someone asked the definition, here's the definition. These tend to be very small compared to 1, which suggests destructive interference is prevalent. Okay, I'll relate that back to protein structure in a few seconds. Okay, so we heard about the pathway model. It's taking this quantum mechanical multi-pathway electronic structure problem and really at the end of the day mapping it onto a graph theory problem. If we know all the distances or transit times between subway stops in a subway system, I can ask what's the quickest way to get from Heathrow Airport to, say, Northeast London. And surely I can walk, I can take buses, I can take the underground, I can swim the Thames and then grab the subway. And they're all associated with a product of those penalty factors that Jose told us about. And so that's a starting point for sure. And the interesting thing about it is that I can take a protein like cytochrome C, and just from the pathway model, I can see there's huge scatter in the predicted electron transfer couplings as a function of distance. A simple exponential is not adequate. So if you want a coarse-grained model like the Hopfield model, it's great. It's going to give you the overall drop-off of rates as a function of distance. But if you care about factors of 100 or 1,000 as you sort of refine your methods and your protein designs, then you really do need to include structure. And it's just as Jose said, it's a matter of directness of the coupling routes. Down a beta strand has fewer, smaller component of through-space tunneling. Helical structure has hydrogen bonds and through-space contacts that make the overall decay faster. And although 1.1 and 1.4 don't look like they're very different numbers, that's a big deal when you put it into an exponential and throw in 10 angstroms of tunneling distance. Okay, so we heard about destructive interference, and one thing we discovered in computing donor-acceptor tunneling interactions in a multi-pathway framework is that if you have lots of pathways, the coupling value goes through lots of zeros. There's a lot of interference, non-trivial interference among the coupling routes. On the other hand, if you have a structure where the tunneling pathway is very direct and not highly degenerate with other similar strength pathways, the zero crossings are much less frequent. So this is consistent with José's story about destructive interference, and if you want to go really fast, you shouldn't be set up with this destructive interference regime. The other comment I want to make is that by looking closely at heme proteins, we find that if you tunnel into an axial ligand in a heme protein, you tend to have sparser pathways. The way that hemes are wrapped up in proteins gives you sparser pathways into the axial ligands than into the heme edge. So this is a typical example showing multiple coupling routes into a heme edge from a surface histidine, as opposed to one of the slow paths into the heme through an axial ligand. Okay. All right, so people have been attaching donors and acceptors to DNA, and I just want to mention these briefly. The experimental data are really interesting. So they drop exponentially as a function of distance, and then they plateau. And for many years, it was thought that this exponential regime was a manifestation of tunneling. And what I want to argue today is that it's not. It's instead a manifestation of the exponential probability of having multiple fluctuating energy levels match one another, and then a resonant transport process. The key experiment that Fred Lewis and others at Northwestern did was they were able to do ultra-fast transient absorption experiments in this exponential regime and find carrier population on the bridge as they varied the length of this AT bridge between two still being donor and acceptor species. So this is a case where a sort of bio-inspired model system was really, really informative. So theory was, the initial idea about these experiments before that transient data was reported was that you had a tunneling mechanism here, rapid distance decay, and an incoherent hopping mechanism at longer distances, consistent with the relatively smaller barriers for injecting charges here. But what we came to realize is that these 10th EV vibronic broadenings that I spoke about could wash out the tunneling, what we would think of as the tunneling barrier in this system. And so I have these many donor bridge acceptor sites, the AT base pairs in the DNA, the bridge sites, and the still being donors and acceptors. And there's a probability of matching them all. And if I have independent fluctuating systems with probabilities for reaching a particular energy regime, the probability of matching them all is multiplicative. And so that also gives me an exponential distance dependence. And then I can propagate my electronic wave packet coherently through that system if that degeneracy lives long enough for the wave packet to move coherently through. So similar in spirit to some of the arguments we'll hear about coherent transport in moving excitons through light harvesting complexes. Okay, and we can set up the theory in a sort of generalization of the Hopfield to Gaussian model. Okay, so we have a tunneling problem with multiple pathways, and it's like the cartoon in the Feynman lectures with a source and a detector and wave phenomena, and we've seen cartoons like this already. We've been wondering whether it's possible to manipulate the coherence of this process. And here, the definition of coherence is kind of simple. It's as though I take this experiment, double slit experiment, and cover one of the slits, and then I cover the other slit. If I cover one of the slits, I'll get this sort of double hump distribution at my detector for the electrons. If I leave both slits open, I'll get the interference pattern, and all the coherent phenomena we've been discussing in electron transfer are assuming that we're in this limit. So we recognize that the double slit experiment is kind of like a double pathway experiment in molecules. So imagine a sort of cartoon model for the double slit experiment reduced to a tight binding picture. So if I have two pathways for an electron to tunnel through a bridge, if I have a marker that's going to tell me which way the electron went, then I should destroy the interferences that you see here, and I should measure electron transfer in this sort of regime as opposed to the coherent one. Okay? So what we thought about was wiring up an oscillator that would either take h bar omega of the electronic energy as the electron went by, inelastic tunneling in other words, or maybe an oscillator that could push h bar omega of energy into the electron. Either way is fine. we worked out the algebra for this, and you can show quite simply that having this vibronic marker of the tunneling route destroys the interference. So we started talking with our experimental friend Igor Rubtsov at Tulane, and first the experimentalists laugh when you ask them to build a double slit molecule for you, but the literature of chemical electron transfer is quite mature, and there are donor, here, nitrogen donor, anthryl acceptor in the photoexcited state is a strong acceptor, and a sort of GC base pair bridge. These molecules had been built by John Sessler at UT Austin, and our friend Igor was able to do a modification of the original electron transfer experiment that had been done. So you can measure unimolecular electron transfer in the system. What Igor did was a 3-pulse experiment. So he photoexcited his anthracene, but very shortly afterwards, with a mid-IR pulse, he excited vibrations of the bridge. So he wanted to see what the influence of these vibrations would be on the electron transfer. Turns out that, interestingly, the rate of charge separation actually slows if you jiggle the middle of the molecule, but the rate going back to the recombination electron transfer reaction actually accelerates. So we thought this was a really interesting observation. The effects are small, factors of 2 to 3, but nonetheless measurable beyond the signal to noise limits. And so our initial thinking was that this would be an interesting either influence of driving geometry-dependent coupling changes, maybe changing the interferences among these coupling routes. We worked really hard for a number of years on this problem, and we found basically the coupling matrix element doesn't care about the mid-IR excitation of the bridge states. And so our current thinking is that this IR excitation is a little more trivial. It's more like a local heating effect. So in the forward direction, indicated by this red arrow, the reaction's nearly activationless. So if I heat this system up, I move the reaction coordinate away from the minimum here and away from the activated complex, the Marcus crossing point. And we think that explains why IR excitation may slow down the forward rate. On the other hand, because of the difference in the driving force, thermodynamic driving force in the two directions, it happens that the recombination event is activated. So we think that IR exciting it is like heating it up and helping you reach the geometries associated with the activated complex. Okay. Just in the last minute or two, I'll mention some intriguing features of 2 electron transfer events. So we heard a lot about flavins, and we heard brief mention of electron bifurcation. So I don't guarantee that they're interesting quantum phenomena here, but I think the physics of these reactions is very interesting. So biology has not only 1 electron donors and acceptors, but also has 2 electron donors and acceptors. And quinones are one of the classic examples. It's a 2 electron carrier. It can be singly or doubly reduced. And there are some very interesting cofactors in biology that will store 2 electrons, and then when they're kind of triggered, will send out their electrons in opposite directions one at a time. And so this is called electron bifurcation. And let's see what I've got here. Right. What makes these reactions, I think, so interesting for this audience, and the reason I present this with very limited data to show you, is that if you go in the laboratory and you measure the redox potential of a fully reduced quinone, you measure the potential at which you pull out 2 electrons, you'll measure an average redox potential. You'll measure one number, which is around here. With this reference, it's going to be at about plus 100 millivolts. But what reactions in biology have figured out how to do, and these reactions occur in complex 3 of mitochondria, and also in other contexts that we heard about briefly. The amazing thing is that the electrons are parsed out at energies that differ by almost a volt, almost as large an energy gap as you have associated with the photoexcited state in photosynthesis after it absorbs the photon. And so these bifurcating electron transfer systems have figured out a way to distinguish between high and low energy electrons and send them out so that the energy that I'm starting with, the doubly reduced state, can be parsed out to create a moderately reducing state and a strongly reducing state. And so I think it's intriguing. We're working on the quantum mechanics. I think it's going to turn out to be a story about proton-coupled electron transfer as much as anything, to sort out how enzymes have evolved to parse out these electrons at such vastly different energies. But the reason I bring it to the attention of this audience is it looks a little bit like a Maxwell's demon sort of experiment, where I've got an intelligent being that's able to look at a thermal distribution of, say, gas molecules, gas atoms, and separate hot from cold, and then use that sort of entropic energy to do some work. It's not really as mysterious as this, because the bifurcation reaction that I'm telling you about here is actually executed with the spending of some energy, right? So it's not separating hot from cold without a cost. There's a price paid by the bifurcating enzyme, so it's not quite that mysterious. Okay, so I think my time is about up. I'll end with this question that one of our friends and mentors and pioneers in this field has asked, or rather a declaration that he made in an annual reviews article that he wrote recently. John said, "The role of quantum mechanics in biology is central but trivial." So this is an enigmatic comment, as so many remarks from John are. So you have to decide what central means. You have to decide what trivial means. So I think it's a good exercise to this group to try and answer this question. Okay, thanks especially to NSF, who's organized the meeting and made much of this work possible. We're also supported by these other agencies, and I think at least 4 out of 5 of them have all supported investigations of the kind that I discussed today. So, so these are really core issues in chemistry, biology, physics, and they're deep issues and very central to what we think about. So thanks very much.
Yeah.
I have a comment, a couple of questions.
Okay.
First, the quantification of coherence has only recently been understood by various groups like Plenio, Adesso in the UK, etc. I come back to your definition of coherence. I might, perhaps I got it wrong, so correct me if I got it wrong. But looking at the definition, it seems to me that you might be underestimating how coherent the whole process is, because it seems like you connect coherence with destructive interference. Is that right?
So for my definition, what I mean by coherence is, in the context of the donor-acceptor coupling, is I'm going to estimate that coupling with a straight calculation that's going to be a Schrödinger equation calculation without any destruction of the multipathway interferences through interactions with the bath, through dephasing interactions. So I'm going to do, maybe another way to say it pragmatically is we take the time series that Jose described of structural snapshots, and for each structural snapshot, we solve the Schrödinger equation to calculate a coupling matrix element. So that would include all of the coupling pathways to infinite order if we do the calculation right. So that's what we are meaning by coherence here.
Okay, just just second question is related. You said in one slide that the process is coherent, but in a previous slide you had 3 time scales. Mm-hmm. Going back to those 3 time scales, when is it coherent?
Right. So let me pull that up. Right. Yeah. Okay. Right. So this is good. Right. Okay. So the first point is that advance it. Right. So the first point is that I can estimate how long the energetic degeneracy lives. So the question is, can I do a straight Schrodinger equation calculation of a coupling interaction? And I would say if I do that Schrodinger equation calculation, it's relevant to this energy pose. Okay, so it's only going to be relevant to that fleeting geometry that's present for about 3 femtoseconds. If the donor-acceptor couplings would change while I sit in that activated complex, then I have to do something a little more complicated. Maybe simplest thing would be a non-Condon calculation. Maybe I need to start worrying as well about details of the quantum dynamics and how I get to the rate. But my point is that the coupling fluctuations, and this is a result of simulation too, the coupling fluctuations are an order of magnitude longer time scale than the time in which I live at the activated complex. So what I mean by coherence is I can solve the Schrodinger equation, calculate a donor-acceptor coupling matrix element in a sort of static electronic structure calculation at geometries, and there are many of them, corresponding to that crossing point. Every time I go through that crossing point, I'll be in a slightly different configuration.
So you're saying coherence survives only for the first time scale?
Let me add just
Sure,
one more thing. I think that maybe our definition of coherence is not what you're calling coherence. What you're calling here is the following situation. We call the fact that now you have these multiple crossings, and we say every time you come through that crossing, do you get a number that's similar or is different? The rest of your entire pathways, the entire thing that changed your term, is the same or is different?
You're referring to your coherence parameter.
It's the same one you use later on, right? So
right.
that's maybe is not what you're calling it, but that's what you're saying in a sense that basically, because what happens is, in order for the electron to tunnel, you have to add a contribution of many of these different crossings.
Yeah.
And the question is how each of these crosses contribute, and that's what you're calling. Are they all helping each other, or they destroy each other? So it's not coherence on your term. It's just a question if they're sort of interfering, helping, or destroying each other. So that's what we are defining.
That's right. So
Bad, good or bad, that's the definition.
What I'm saying is, it might, if you want to say is coherent or not, maybe it's more coherent than
a better way to summarize José's coherence parameter is it's a measure of whether destructive interference among the pathways is playing a role or not. So the word coherence was used in two contexts in my talk. One related to the calculation of the coupling matrix element in the degenerate states, and the other in the context of his coherence parameter. Yes.
So I have a slightly different question. So does this have anything to do with biology?
Absolutely.
I mean, in actual environment in water, 10 picoseconds is the time at which the oxygen and hydrogen atom fluctuate in the water molecule. So I don't know.
Oh, well, there are a couple of answers to your question, or it has a few layers. So one is, does the structure of the pathways matter? The answer to that is yes, because if you're, let me finish. Let me finish. So if the electron transfer rates are accelerated or slowed by a factor of 10 or 1,000, it can be lethal, right? Or the reverse. The second issue is about whether the detailed quantum mechanics of the interferences matter. So José's argument is if you want to go really fast out of an excited state, you have competing energy wasting processes. You don't want to have to jiggle around to find a geometry with a large HDA, a large coupling matrix element. You want to be able to go as soon as you prepare the excited state. So for biological function in ultra-fast ET, as in primary charge separation, it probably is a big deal that you have a large value for the coherence parameter, that ratio there. Mm-hmm. So I would argue yes.
I mean, I just
No, but
let me just ask a question because I don't think it was the
But I mean, Ed, I know what you're asking.
My problem is actually that I would never cross my mind to do a simple Schrodinger equation for electron tunneling in a complex environment inside.
It's now a cottage industry.
No, I understand.
Yeah.
the industry.
Okay, go on.
Because I'm not part of it, I can ask that
Okay,
question.
sure.
I mean, I have much simpler systems, and I have to use
No,
like
just
complicated density matrices or go to DFT
Sure.
or do actually a real calculation, rather than this simple, to me, seems like toy models, which probably happen.
So what you see is a sweep from toy models to actually supercomputer calculations.
Okay, so
all in both of our talks.
So the question is, first of all, I'm telling an answer about the calculation. The other is the importance for biology. What we show is that basically, when we started to do these calculations on proteins, it was impossible to do a big calculation. So we defined what you're calling a toy model, a very simple model. What I'm used as afterwards is that those calculations agreed more with experiments than if you did a full DFT with a frozen protein. Then we were able to come to explanations that basically you have to wait for this path to come to a case where all these pathways help each other. So in a sense, that's one point, to figure out why the dynamics of the protein, or people call noise, becomes an important thing to say you have a few paths dominant. Now, when you have a few paths dominant, electrons are always tunneling. The question is now, what is important for biology? When the tunneling is important? When you have a reaction, the tunneling reaction is the most important thing for biology, then biology that becomes very important. So the charge separation photosynthesis, control that tunneling and make it fast and make sure the pathways help each other, was evolutionary select by biology because you need to get these things. But when you have two other tunneling energies, like I said, between the quinones, which is not important, there was no selection by evolution to it. Even so, there is electron tunneling there. You can say it's relevant for that biological process. Even so, the electron has to tunnel. Other processes are the important ones. So what you observe is there are a few select cases. That's what Hopfield, in my point of view, Hopfield calls trivial. It's central because the charge separation requires it, but it's trivial because there's a real explanation. If you have to separate charges on times faster than picoseconds, that's the only choice you have. So that's the case where quantum mechanics is important. So go back to when is quantum mechanics important. Taking out chemistry, taking out chemical reaction and catalysis, it happens on events where they are very, very fast, that we know that quantum mechanics is important. One is fast charge separation. The other one is vision. These events have to happen on very fast time scales. Then you have to have a biological control of them. But the other things is not clear if they're important or not important.
This is getting back a bit to the definition of coherence, but perhaps in a different way. It seems that when you have this donor-acceptor coupling that's much larger than the fluctuations, it would be something more like a delocalized state, if we wanted to think of it that way. Is that a valid way in your mind to think about it, that the states, the Hamiltonian eigenstates, the energetic states, the ones that would be expressed with a delta G in a typical Marcus theory, are actually delocalized across the system, either instantaneously or if it's persistent and therefore a larger coupling element than the noise, done in a more permanent fashion?
So what I would say is, if the energy barriers are the same order of magnitude as the energy fluctuations, then there will be temporary resonances instantaneously, so that you can't assume that tunneling is the dominant mechanism. In the case of proteins, in the typical cases anyway, where the barriers are a few electron volts, that seems to be the case. But as you get to pi electron bridges, like you see in DNA and in synthetic systems, even in structures with stacked aromatic side chains, perhaps, then you could start to question whether the deep tunneling picture is the right starting point. Yeah, I think we agree.
So that we agree. I think Dave, two things here that I think I just want to clarify. One, that Dave was clear that basically the gap you're talking about proteins, typically are 2 electron volts. On DNA is 0.2 electron volts. So in a sense, you can avoid some things, you can afford in some reactions to wait for thermal fluctuations to excite you to those states before you go. If the distance is very large, the thermal excitation is a possible situation that he's showing in many cases. In electron transfer, you cannot do that. You don't have the time to do. The other one is maybe our ill-defined coherence factor. These things was defined 15 years ago, 10 years ago, much before the modern definition of what people call coherence, is the fact that you always have this constructive destructive interference. On the cases where you have to have a fast electron transfers, you tend to stay with very small fluctuation about this matrix element. Then your TDA square is good. You run into trouble on situations where these things haven't been selected properly. So you can oscillate from you can switch the sign of TDAs. And that's not the switch the sign that's the problem. It's crossing the zero. If you spend too much time around the zero, that's when you lose contribution. That's when you have on the quinones. Right? And we crawl these things to say that basically these contributions are not helping each other. They're destroying each other. And if you spend most of the time there on the crossings, then you are in trouble. That doesn't happen on the case when you have to have optimal fast electron transfer, And you observe that, and that's where single pathways work. Right? When I show the quinone case, single pathways really fail because you look the best pathway. That's not the one that dominates it. So what you're very curious in the past is why for this important biological electron transfer, such a simple model, or if you want to go to Creston mode, toy model, survive as being predictive and used by many experimentalists. So it's a situation, that's where the situation comes that becomes important.
Yeah, maybe I could summarize this by saying there's always going to be a set of competing timescales. So let's say we're doing photosynthesis and we have the special pair in a photoexcited state. We need to separate charge faster than I'll radiatively or non-radiatively decay to the ground state. If I happen to be in a destructively interfering pose and I can fluctuate away from it fast enough to beat those deactivating processes, then I can live with destructive interference. If I can't, if I don't fluctuate into the strong coupled pose fast enough, then it's going to kill me. And so there's a selective pressure. So there are always competing timescales.
But
in all
also
these
the other
processes.
time you didn't raise here that goes to his case, it's what you call the traversal time, the instanton time that goes across. And basically when you get to cases where that's important, then you have to put, you get to do non-Francondo effectors that you call in the situation, you have to correct for that. Doesn't appear to be the case here, based on what they just...
And we've done simulations. They seem to be on the tens of femtosecond timescales. They arise from dihedral motions of the protein in our simulations of azurin. Probably they're very important in the pi electron systems and the DNAs and related. Yeah.
So what is the source of the 0.2 volts fluctuations?
It's vibronic interactions with the medium. It's the
Most
Marcus
polarization.
polarization. Yeah, it's medium
But
polarization
it's
fluctuations.
KT. It's KT.
Well, it's coupling of
But-
it arises from the fact that opposite charges attract, fundamentally. It's the electron influence on the nuclear motion, right? The motion of the electron causes changes in the bond lengths and bond
So
angles.
first of all, you have to...
It's the Marcus,
let me add a
it's
couple
Marcus
things.
reorganization. energy.
That comes to
And KBT as well, it's the product.
That comes on how much the medium has to reorganize as you move around. So if you do a lot of electron transfer in very polar medium, that reorganization energy is enormous because taking an electron for polarization. When you have to have fast electron transfer, like on the case of proteins when you go between bacterial chlorophyll and pheophytans, if you have a look on that protein, they tend to be as non-polar environment as you can because the system wants to be fast, so you don't reorganize the medium too much. So you observe that lambda goes from numbers that on polar medium, that reorganization energy tend to be 0.4 electron volts to numbers that are more the order of 0.1 electron volts.
But what polarizes the medium, that's what I'm asking.
If you have an electron here, and now I put an electron there,
But why is the electron, I mean, I don't understand the whole thing.
It's
So you're sitting there, you're not doing anything, a photon comes
So,
out.
well, the
No,
protein has a
let-
dielectric constant at the very least, so you understand it
Creston,
from that
there's no
perspective.
equilibrium. There's no equilibrium.
I think, gentlemen,
Thank you.
Okay, let's put it this way. Let's put it this way. If you have photosynthesis, you're getting confused. If you have photosynthesis, if you get photosynthesis, you have a state here. A cytochrome come here and put an electron there. If there was no medium and the states are resonance, then you reach on quantum mechanics, a two-level system. You could find a ground state, go back and forth. Right? You just inject an electron in one particular situation. That's what happens in photosynthesis. The electron comes from the cytochrome C goes in there.
Joseph,
You could
Joseph, I'm
think
sorry.
of this as a small polaron.
No,
if
hold
you